Hello, I hope all of you are having a good Friday. Make sure or don't forget to listen to this video before coming to class on Monday. So let's go straight into it, deal with basic terminology. First one we're seeing is micromechanics. What does it mean? It means that we are going to start from the components of a composite, that is the fiber and the matrix. And then we are going to use those individual properties to calculate or determine the properties of the composite lamina. That is called micromechanics. Macromechanics, on the other hand, is a high-level analysis of the stiffness, strength, etc. of a given lamina. It can be unidirectional, bidirectional. If it has fibers in a single direction, it's called unidirectional. If it has fibers in two different directions, it's called bidirectional. So at this level, we just consider it as a single material and average out the properties instead of looking at it from a fiber and resin point of view. And then are composite materials isotropic and are homogeneous? By this point in your degree, I hope you know what isotropic means. It means the properties of the given structure or material are all equal in all directions, right? Example is metals, right? All metals are isotropic, but concrete is not. Homogeneous is similar, but it is not the same. It doesn't talk about properties in all directions. Rather, it says that a homogeneous body has the same properties at all points in the body. So usually we consider composite laminates to be homogeneous and not isotropic because of the way everything is aligned, you definitely don't get equal properties in all directions, but you can average it out and say the properties are the same at all points in the body. And lamina is made out of fiber and resin. All of us know that. If you stack lamina together, you create a laminate. Hybrid laminate, meaning you mix and match. We will see what are the different types. For example, interply hybrid laminates, meaning it contains plies made of two or more different composite systems. Lamina is also called a ply. Okay. For example, in cars, car bumpers are made of a mixture of glass epoxy layers and graphite epoxy layers. Graphite epoxy gives stiffness, glass epoxy gives torsional rigidity, meaning twisting rigidity. Intraply hybrid composites consists of two or more different fibers used in the same ply. That is, in the same resin, same layer, you mix two or more different fibers. For example, in golf clubs, you have graphite for torsional rigidity and aramid is mixed with it for tensile strength and toughness. Aramid is very costly compared to graphite. Graphite itself is costly, but golf is an expensive sport, so you have a combination of graphite and aramid. And then you have an interply and intraply hybrid where you can mix and match. And then there's resin hybrid laminates where you combine two or more resins instead of fibers. And usually how you pick is you pick one resin to be flexible, the other one is a rigid resin. So this mixture increases shear and fracture properties by more than 50%. This is important because resins are the one that determine the composite's properties in terms of shear and fracture. So how does a typical laminate look? Each lamina is usually, the thickness is 0.125 millimeters and you stack them up to get a laminate. So this is a laminate, right? And each layer is a lamina or ply. And you can see how the fibers are oriented differently in different plies. So a real life example is the leaf spring suspension system that is used in a variety of vehicles. So this is usually, surprisingly, it's not made out of metal. It is made out of composites because as we saw earlier with all the golf club and car examples, it gives a pretty good torsional rigidity and also tensile strength. So, what is the difference between an isotropic plate and a composite plate? If you have, let's say, a metallic plate, and look at case A and case B, both are undeformed. Let's say you have a square plate and then you pull at it in this direction, right? So it lengthens in one direction and it reduces in the other direction. This we already know from solid mechanics, right? But what we notice is if you, instead of loading in the horizontal direction, if I load with the same load in the vertical direction, it grows in the other direction and thins in the second direction, correct? This is what happens. And we also see for an isotropic material in this case, sorry, my bad. Okay. What's happening? Let me go back, come here. Okay, there's something wrong with the presentation itself, no problem. Let me tell you what I meant to say. Let's just get the picture. So what I was trying to say is that if these two cases are observed, you see that in the first case, the lengthening, right, is equal to the lengthening or deformation in the second case as well, right? You can see that how much it lengthens under a load is independent of direction. Similarly, how much it shortens or reduces in the transverse direction is also independent of the direction. So that is the characteristic of isotropic materials. But what happens if it is a lamina, unidirectional lamina? If you do the same thing, what we observe is that depending on the loading direction, the values are different. Okay, something is wrong, but you get what I'm trying to say, right? In this case, the first case, let's say one direction is lengthening, which is delta 2. Delta 2a is not equal to delta 1b. Delta 1b or deformation delta 1a, which is shortening, thinning in the one direction in the first case, is not equal to how much it reduces in the second case, right? The properties are dependent on directions. Properties or behavior are dependent on the direction. Dependent on direction of loading. Why? Because in whichever direction you have fibers, that direction is stiffer or stronger, so it doesn't displace or deform as much. But in the direction of the fiber, which in this case would be like this, the fibers are not oriented in this direction, so it is relatively weaker, right? That is why usually we use a combination of plies. And particularly if you have plies that don't go horizontally or vertically but at a different angle, then you have additional shear or twisting of the structure also in addition to your normal displacement. So all of this makes the analysis or characterization of composite materials complicated. The basic is still the same, but how we go further from that, we have to build from the foundation of solid mechanics. Okay, so stress. If you were in my class, I keep telling people that if you're a mechanical engineer, even if someone shakes you and wakes you up out of sleep, you should be able to say what stress is. Stress is force over area, that is internal member force by cross-sectional area, right? So for example, if let's say you have a cross section and you have an internal member force delta P, which you can resolve in all the three different directions, you can see that one of them is normal to the surface, normal, and the other two are going along the surface, which means they are shear forces, right? So how do they look? And why this keeps happening? Sigma x equals limit delta A tends to 0. I think it's something to do with my iPad, but that's okay. Tau xz equals limit, the same thing, delta A tends to 0 because we are talking about a single point, Pz divided by delta A. It is still force over area. And then stress is comparatively simpler. If you remember from solid mechanics, if you consider any point in the material like an infinitesimal cuboid, you have normal stresses going in all three directions and correspondingly shear stresses on all faces. But what we observe and what we can prove experimentally is that, I hope this works, it doesn't, so let's do this. Let me write. What we have observed experimentally is that tau xy equals tau yx. You can actually derive it. I don't remember if we did it in solid mechanics though. Tau xy equals tau yx, tau yz equals tau zy, and then tau xz equals tau zx. As you can see from the picture, the first letter in, for example, in tau xy, x is which direction? X is the normal to the face. That's the way we write shear stresses, direction normal to the face. And then y is the direction of the stress. Direction of the stress. Right, this is how we write it. And all of these stresses are equal. This makes our life comparatively simpler. Instead of finding a lot of unknowns, we can actually reduce our stress tensor to limited number of unknowns. But where it gets more complicated is strain, because even if you apply a simple tensile load, you have shear deformation also. So let's start with the basics. Let's consider u as the displacement in x direction, v is the displacement in y direction, w is the displacement in z direction. So if you consider normal strain in the x direction, limit AB tends to 0, and we know the definition of strain. It is change in length divided by original length, right? And if you see from the picture here, it gets more complicated. AB is equal to, or it's not AB actually, it's the deformed A dash B dash. I'm pretty sure it's something wrong with my iPad. A dash B dash is equal to root of A dash B dash square, or A prime B prime square, and B prime B prime square. So then if you look at it geometrically, AP, this is the A prime P prime. So this, sorry. Okay. It's changing. Okay. So if you look at this one, you see that this is u of x comma y, how much the point x comma y has changed, and this point is x plus delta x comma y, correct? So then this point is u of x plus delta x comma y. So the length of A dash B dash is the difference between how much they have moved, so u of x plus delta x comma y minus u of x comma y, but you of course don't forget to add the initial length of the side. Plus b dash is simpler, it's just b has moved up, so it's v x plus delta x comma y minus v of x comma y, because a hasn't changed, so it's just v of x plus delta x comma y and v of x comma y. So then AB is delta x, the original length. If you do substitutions, as you can see, there's a lot of missing letters here. Let me fill it out for you. X plus, okay, x plus delta x, I believe. No, why it is this way, maybe because of the book, but we're not bothered with the whole aspect of that. Let me fill out the brackets first, those are more important. Square, square, and then whole square root minus 1. If you sit and work on it, you will get it, but you don't need to. But if you simplify it, what you get is 1 plus dou u by dou x square. So this is the partial derivative part of our mechanics, right? So this is what you get. 1 plus dou u by dou x square plus dou v by dou x square root minus 1. But what we can say is we are assuming small strains. So if you assume small strains such that dou u by dou x is very, very less than 1, dou v by dou x is also less than 1, you get this square gets cancelled out because it's already less than 1, and 1 plus dou u by dou x the whole square and the square root cancel out, 1 cancels out. So ultimately you're left with epsilon x, or strain in the normal strain in the x direction, is equal to dou u by dou x. Similarly, strain in the y direction is equal to dou v by dou y, how much it has displaced with respect to the y. You might ask, if u is the displacement x direction, v is the displacement in y direction, why do we need partial derivatives? It's because one is not independent of the other. I'm not going to go through the derivation, you don't have to, but if you're interested, you can definitely look it up. It is there in your textbook. I don't know why my video is so bad for this. I apologize. But the concept of it being, it's the same policy. Since it's shear strain, you should know this from solid mechanics. Gamma xy equals theta 1 plus theta 2. How much the two sides have gone through angular deformation. So based on the same principle of what we used for our normal strains, we do the same process and you get, yeah, writing theta 1, theta 2. So here it's delta y. Substitute everything. I'm pretty sure the equation here is incomplete, but don't worry, I've got you. And this is also there in your book, so you don't have to look at this, and when we look at it in class, of course it will look better, I promise. So gamma xy is a combination, and you can see why we are using partial derivatives here. Just like we did the last time, we assume all the strains to be small, and you're left with gamma xy equals dou v by dou x. You can see the displacement in y direction is also dependent on x, and similarly the displacement in the x direction is also dependent on y. So this is what your shear strain is. So I have a picture, so that works here. This is what our normal strains and shear strains ultimately look like in terms of partial differential equations, right? So based on this, we will do problems in class, and we will also talk about different kinds of materials and how this stiffness and compliance matrices, I know those are new terms, but basically stress and strain relationships change for different materials. All right, I will stop here. Please go through this video and come.